Good morning, everyone. Today, I, Jyotika Tuteja of Pandit Jawaharlal Nehru College, will teach you about groups and rings. In the earlier video, we were doing examples on the groups, okay, how to show that a set forms a group, or we can say an abelian group. Let's start for the further examples. Let's start with example number 4. What is the question? Let M3 denote the set of all 3x3 non-singular matrices. Show that it is a group but not an abelian group with respect to matrix multiplication. So for showing a set to be a group, we need to show the 4 properties. The first property is closure property, which says if we take 2 elements of the set, let A and B belongs to M3, then A cross B will also be a 3x3 matrix. Obviously, if we multiply two 3x3 matrices, then it will give a 3x3 matrix which will belong to our set, which is M3. So the closure property is satisfied. So let's move on to the second property, which is associativity. Matrix multiplication is associative, that is, if we multiply 3 matrices in whichever order, the resultant will be same. So it follows the associative law. Third property is existence of identity. We need to find a matrix such that whichever matrix is multiplied by that matrix, or we can say identity matrix, then we get the matrix itself. So here, for the existence of identity property, we have our identity matrix as identity matrix of 3x3 order will be our identity. So the fourth property is existence of inverse. For an inverse of every matrix of 3x3 non-singular matrix, we need to find such a inverse such that if we multiply the matrix with its inverse, it will give us the identity matrix. So obviously we have non-singular matrices. Non-singular matrices means that they have their determinant as non-zero. So a matrix which has determinant as non-zero means it is invertible. So there will always be an inverse of the 3x3 non-singular matrices, which we can denote by A inverse, and we know by the definition of inverse that it satisfies the property A into A inverse is equals to A inverse into A is equals to identity. The next, here we have already proved the 4 properties. That means we have proved that our set M3 is a group. Next, here it has written that we need to prove it is not an abelian group. So basically we need to prove that it doesn't satisfy the commutative law. Let's see. Matrix multiplication is not commutative. We already know that if we multiply A cross B and we multiply B cross A, so sometimes it is not possible to do both the cases. So obviously it won't be equal, and sometimes when it is possible to do both the cases, it may occur that they are not equal. So matrix multiplication is not commutative. That means AB is not equals to BA in all the cases. And when we are proving something, we need to take all the cases. So we have proved our 4 properties, which satisfies and proves us that M3 is a group, but it doesn't satisfy the commutative law, so it is not an abelian group with respect to matrix multiplication. Let's move on to our next example, which is G, for the set G, which is a matrix set in which we have matrices of the kind A0, 0, A, where A is a non-zero real number. Show that G is a commutative group under matrix multiplication. So here we have our binary operation as matrix multiplication, and set has elements in the form A0, 0, 0. So let's start. First property is closure property. Let A and B be any matrices of the form which are in G. So they'll be of the form A0, 0, 0 and B will be B0, 0, 0. So these are the two matrices. Let's multiply those matrices. When we multiply those matrices, we get AB00. So our matrix A into B belongs to our set G. So it satisfies the closure property. We write it as G is closed with respect to matrix multiplication. The second property is associativity. We already know that if whichever matrix it is, if we can multiply those matrices, then the order in which we are multiplying three matrices doesn't matter. In whichever order we multiply it, the resultant will be same. So it always satisfies the associative property. So let's move on to the third property, which is existence of identity, where we have E as 1 0 0 0. Let's multiply it with a general matrix A, which is A 0 0 0. If you multiply it, then we get our A itself. In the reverse order as well, when you multiply A, E, and we calculate it, it again gives us A matrix. So here our identity matrix is 1 0 0 0. Fourth property is existence of inverse. We need to find an inverse for each and every element. We already know that the existence of identity element is for the whole group. But for the existence of inverse property, inverse element is particularly for a one element. That is, inverse is calculated for each and every element of the set, but identity element is for the group itself. So let's start. We'll take an arbitrary matrix A000, and we'll calculate the inverse for this matrix. Let's take B as 1 by A00, where 1 by A is non-zero because A is non-zero. So B belongs to our set G. If we multiply A into B, then we get our identity matrix E. And if we multiply B into A, then again we get our identity matrix E. So AB into BA is giving us the identity matrix for the set G. So we can say B is the inverse of A. So in this pattern, we can multiply each and every inverse for every element of G. Last but not the least property, our commutative property. If we multiply A into B, then our resultant will be AB000. If we multiply BA, then again it is coming out to be AB000. So commutative properties, sometimes when we take particular cases for the matrices in such as this one, where we have taken set where elements are of a particular form of a matrix like A000. So we have a particular form of a matrix. In this particular case, our commutative law satisfies. So in this case, we have our set G, which forms a group, or rather we can say a abelian group, because it satisfies the commutative property. Let's move on to our sixth example, in which we have taken integral values, or we can say the integral powers for an element A. Integral powers are basically the integers. So we have taken a particular element, or we can say an arbitrary element A, which is fixed and it is non-zero real number, and we have taken all the powers, all the integer powers of A. And obviously it's an infinite group, infinite set, and we need to show that it is an infinite abelian group with respect to multiplication. Let's start. In proving for a set to be a group, we just need to show all those five properties. If it satisfies all those five properties, then it is a group. If it doesn't satisfy any one of those five properties, then it is not a group. All those five properties are satisfied, then only we can say that the set forms a group. Otherwise it won't be forming a group. Let's start. Here we have the set G, which has all the integral powers of A. We'll take particularly three elements x, y, z. So it will be of the form a to the power m, a to the power n, and a to the power p. So let's start with the first property, that is closure property. If we multiply x into y, we get a to the power m into a to the power n. That is a to the power m plus n. And if we add m plus n, those are integers. Then adding to integer, we get an integer. So a to the power m plus n will also belong to our group G. Next is associativity. Let's start with x into y bracket into z. So x into y is a to the power m plus n, and next is a to the power p. So we get a to the power m plus n plus p. So the resultant is a to the power m plus n plus p, and we can write it as a to the power m into a to the power n into a to the power p, bracketing over a to the power n and a to the power p. So we get a result of associativity. It follows the law. So associative property is satisfied. Next is existence of identity. Existence of identity. So we have our number a to the power 0, which is 1, which belongs to our set G. So if we multiply 1 with any element that is of the form a to the power m, then we get a to the power m only. So here for this example, we have 1 as the identity element. Next is existence of inverse. So for each element of G, which is, let's take x, there exists a unique element 1 by x belonging to G, such that if we multiply x into 1 by x, we get a to the power m into 1 by a to the power m. So we get our identity element 1. So 1 by x is the inverse of x. So for this set G, we get inverse element for each and every element of G. So it satisfies the fourth property. Last property is commutative. If we multiply x into y, we get a to the power n plus 1, which can also be written easily as a to the power n plus m. So we get our y into x. So commutative property is also satisfied. So here all the 5 properties are satisfied. So we get that our set G, which is integral powers of a fixed non-zero real number, forms an abelian group, or since it's an infinite, we can say it forms an infinite abelian group. So that's it for now. We have done 3 examples in this video for proving that a set to be a group. For the next, we'll do some more example for more practice of how to show that a set, finite or infinite, is a group or an abelian group. Thank you so much.